Let's look at norms on a unit circle. This is going to give us an idea of what the magnitude of some of the norms are with respect to one another. And I've got graph paper up as my background for a reason that will become clear soon, because we're going to be drawing some graphs, and I'd like to be able to show how individual tick marks of where these norms pop out and how they're going to be able to relate to one another. So let's let x1 and x2 each range between -1 and 1. I want to chart the 1 norm of x, the 2 norm, and the infinity norm. And I'm going to use these colors to show how these norms are different in terms of their magnitude for the same kinds of circles. And I'm going to be calling these unit circles even though some are not circles, as you'll see. So I've gone ahead and drawn out x1 and x2 as the axes, and I've shown the range that I'm permitting these values to be. So what we're going to be doing is finding x1 and x2 such that the 1 norm, the 2 norm, and the infinity norm are all equal to 1. That is to say, if I'm going to choose x1 equal to 1, then I need to find x2 such that the norm of x2, x1 equals 1. So actually this is only true if x2 is equal to 0. Let's do a couple of more examples and see how this looks. Oh, and by the way, the reason that this is true, in case you forgot, is that the 1 norm is the sum of the individual elements. So here we're choosing individual values of x1 and x2, and the 1 norm is the sum of their absolute values. So in order for that sum to be equal to 1, if I've already chosen one of their values as 1, the other value must be 0. So let's do this for a couple of more points. If we choose x1 equals to 0.8, then x2 has to be 0.2. If we choose 0.6 for x1, that gives us 0.4 for x2. And likewise 0.5 for x1 gives us 0.5 for x2. So we can plot these dots over on the right hand side as well, and we see a fairly, probably foreseeable pattern showing up. And we can do a lot better than choosing individual points. I mean, we're engineers after all. This is a math class. So let's actually calculate what's the equation that's going to give us the norm in this quadrant. So this is, to remind yourself, for 2 elements, this is what the 1 norm looks like. It's the sum of their absolute values, and we're requiring that 1 is the magnitude. That's what's going to give us what we're calling the unit circle. So in quadrant 1, this is going to be x2 is equal to 1 minus x1, which we can draw as this line. In quadrant 2, x2 is 1 plus x1. That's because x1 is negative there. So we can change the sign and get this actual line that describes its behavior between the 2 axes in quadrant 2. So I'm going to clean this up a little bit here. For quadrant 3, x2 is equal to minus x1 minus 1. And for quadrant 4, x2 is equal to x1 minus 1. So we end up with this unit circle, which is sort of like a circle, but not really. It's a square that's been rotated by 45 degrees, or you can think of it as a rhombus that's ordinarily rotated. So that gives us the unit square for the 1 norm. And again, we've defined the unit square here as the square where the magnitude is 1 at all times. So let's look at the unit square for the 2 norm. How do we define the 2 norm, in case you've forgotten? Well, the 2 norm is equal to the square root of the sum of the squares of the individual elements, which gives us the square root of x squared 1 plus x squared 2. And you might actually recall that this is a circle of radius 1. So we can actually go ahead and draw that circle here, and we can see that the unit circle for the 2 norm is bigger than the unit circle for the 1 norm, or equal to at the axis points. The infinity norm is the maximum value of the individual elements. So if we choose the maximum value of 1, we actually get a range of values of x2 if we've chosen x1 is equal to 1. So it's actually true for all values of the magnitude of x2 less than or equal to 1, which is this whole line up and down here. So we can choose any value of x2 that we like as long as x1 is equal to 1, as long as it's in between minus 1 and 1. So we can change a couple of signs here. Let's set x1 equal to minus 1. Well, the range of values for x2 is actually the same. If we change from x2, so for x2 is equal to 1, we can choose any value of x1, and we're going to get that. So that gives us this horizontal line here. And likewise in the bottom, we get this line. So this gives us the unit circle for the infinity norm. Every point on this unit circle has norm value of the infinity norm equal to 1. And we can see that the unit circle for the infinity norm is bigger than the unit circle for the 2 norm, is bigger than the unit circle for the 1 norm. So what does this tell us about the magnitudes of norms? Well, what it tells us is that the 1 norm is always bigger than or equal to the 2 norm, which is bigger than or equal to the infinity norm. Really? Is that what this tells us? Here, this is the 1 norm. It's clearly smaller than the 2 norm and the 3 norm, or the infinity norm, right? Not really. The unit circle for x1 is smaller than the unit circle for x2. And so, for the same values that give us x2 is equal to 1, the 2 norm equal to 1, the 1 norm is actually going to be much bigger. So let's look at this for example. Here, at this point, this is about, let's make it a little bit closer. This is about 0.8 for x1, 0.6 for x2. If we find the 1 norm of those two values, 0.8 plus 0.6 equals 1.4. So the 1 norm is actually out here somewhere. Maybe even out here. For the same values, the 1 norm is going to be bigger. So in a sense, the scaling element, the value for which all of these values are going to be scaled in this coordinate system, is smaller, which means all of those values will inevitably be bigger for the same inputs. So this is why the norms are scaled in this way. Why we always see that the 1 norm is bigger than the 2 norm will be bigger than the 3 norm, all the way up to the infinity norm. So why do we care about this? Well, we care because we can perhaps over-approximate some signal. So we may not know a lot about its signal, or it may be really complicated to describe, but we can, for example, say, I'm going to treat this signal like its infinity norm. And if I can treat it like its infinity norm, then I can show some property about it. Well, the infinity norm is never going to be the best case. I'd rather actually say that the 1 norm of this signal, if I can control it for the 1 norm, then it must be true for the 2 norm, because the 1 norm is bigger than the 2 norm. So we're going to be using these ideas of norms to over-approximate our system and show for the worst case it must be true. Therefore, for other cases, it will be true as well.